Okay, so in the ProSurf project, this was a joint work contributed by KO Leuven and Formatec Ceramics from Netherlands. So in this talk, I will discuss more about micro-EDM based surface structuring and an niobium carbide mold material, which we introduced for improving the performance of a ceramic injection molding process. So in this presentation, I will start with the basic introduction of process chain, which is used in ceramic injection molding at our industrial partner Formatec. This will be followed by the mold surface structuring approaches, which we applied in the framework of this project, namely microabrasive blasting. This was the initial step to evaluate whether surface structuring is really beneficial for this process or not. Then the second step was to use micro-EDM process for doing, let's say, manufacturing micro dimples on the mold surfaces so as to increase the feedstock flowability. And finally, in order to, let's say, decrease or reduce the mold wear during ceramic injection molding, we introduced the novel material niobium carbide. So if we look at the process chain for ceramic injection molding at our industrial partner Formatec, we start with a mold material, which is subjected, it's a blank, so it's subjected to EDM, then subsequent grinding and polishing, and then we get the final insert, which is put into the ceramic injection molding machine. And then we have a feedstock, which is, let's say, coming into the machine, and we get the green part, which is subjected to debinding, sintering, and then the final part. So as you can see here, this is a 3 millimeter ceramic cap, which was the main demonstrator in this ProSurf project. This ceramic cap is made from POM binder with some zirconia particles, and it finds application in high temperature sensors. So in the framework of this project, we introduced two technologies. The first one was surface structuring technologies before the insert is sent into the machine. So in this project, we introduced first microabrasive blasting, which was an initial step, so followed by micro-EDM texturing of the, let's say, the molds. Then another contribution in this project was introduction of niobium carbide for wear reduction. So as I mentioned, the ProFlow demonstrator is basically a sensor cap, which is used for high temperature sensor applications. So with our industrial partners, some of the key issues were the incomplete cavity filling. So as we can see on the bottom right-hand side, that even with a perfectly smooth mold, the surface of the product was highly irregular. So even with the smoothest mold, the flowability was not improved. And also we can see that the wall thickness was uniform. So these are the CT scans of the molded products from ceramic injection molding. The second issue was the energy consumption, so the higher injection pressure. And the third one was mold wear. So it's not a plastic injection molding, it's also having zirconia particles. So it's ceramic injection molding case. So with the normal steel molds, we were experiencing, let's say, higher mold wear. So the first thing which we applied was microabrasive blasting as a mold structuring technology. So to compare what kind of, let's say, blasting approach is good for our mold, we tried two steps. The first one was a single step blasting approach where we used alumina particles. And in the second step, a two-step blasting procedure was used where we blasted first with alumina, followed subsequently by zirconia particles. So we can see in these pictures on the left, we can see alumina particles. They have very sharp morphology, whereas on the right-hand side, we have zirconia particles, which have sharp morphology. So the blasting of the mold surfaces were conducted by both of these two approaches. And we can see the mold surface, how it looks like from the SEM images. So the part one, it's blasted only with alumina surface. So we can see the three different images at three different magnifications. And at the bottom side, a surface of the mold, which has been blasted with, let's say, two-step procedure. So the first blasting with alumina, followed by blasting with zirconia. So we can see in the second SEM pictures, let's say the bottom SEM pictures, that the peaks were killed. And also, let's say the sharp peaks were reduced. We will quantify it more from the measurements which we performed in the subsequent slides. So first we tried with the normal metrology techniques, and we found out that it's very difficult to distinguish based on the conventional parameters like RA and SA and RZ, SZ, RQ, SQ, and so on. So we were looking to find a distinguishing parameter through which we can distinguish the functionality differences between these two surfaces. So at the industrial partner Formatec, they have observed that the part two, which has been blasted with a two-step procedure, was generating better results, promising results in terms of flowability of the feedstock. So to quantify this, we did AFM analysis. So we did AFM measurements and used a hybrid parameter called SDR. So this parameter is basically the ratio of effective area contributed by the texture to the area of a leveled surface, basically. So if it's a completely leveled surface, the SDR would be 0. But if it's, let's say, textured surface, higher the slopes, it will keep on increasing. So here, I mean, it takes into account both the vertical height and also the lateral spacing of the features, let's say in a measurement acquisition area, basically. So first we did measurements with AFM on the mold, which was only blasted with alumina particles. So here we can see that the SDR value was around 11%. And we can also see in a given sampling length, we can see that I will also show for the second part in the next slide that here we have more number of peaks and also the sharper peaks in a given sampling length. But when we did two-step blasting, the SDR value reduces to only 3%. And also we can see that the number of peaks is reduced and the sharpness of the peaks is reduced as well. So this is a very good indication of the functionality of this mold, that with the two-step blasting, the SDR value reduces to 3%. That means effective area contributed by the texture is reducing and we have less contact area with the feedstock. Therefore, we reduce the friction and hence we get better flowability with this kind of, let's say, surface structuring technique. And this technique was also applied on the real molds in the framework of ProSurf project. And the results for industrial partners revealed that we are getting 150 bar reduction, let's say, in the injection pressure when using a two-step microabrasive blasting procedure. That is first with alumina and then with zirconia. To check the repeatability of this, let's say, the result, our industrial partner, let's say from single mold, we can have 4 cavities. So industrial partner used a special marking scheme so we can recognize where is the marking on, so what is the source cavity of this product. So they recorded, let's say, the injection pressure for all 5,000 shots. So it's 1250 around for one cavity. So we have 4 cavities in one insert. So it's around 5,000 shots. And we can see that the injection pressure was nearly constant, around 1500 bars. So the results were promising. So we decided to go for further improvement because with the sandblasting or microabrasive blasting technique, it's difficult to control the distribution of the texture. So the texture is more or less stochastic. So we were looking for a more deterministic technique to do this. And here, based on the long experience of Leuven in this technology, we proposed microEDM surface structuring to get better flowability of the feedstock. So to perform microtexturing on spiral molds, we used a Sarix microEDM setup. So it's a 3-axis microEDM machine. So you all know microEDM is based on the principle of spark erosion. So we remove material by spark. And we have on-machine wire electrode dressing grinding technique. So with this, we can also, let's say, customize the tool diameter, which is not available in standard sizes with the supplier. And first, we tried this approach on a spiral mold, basically. So in order to test flowability, we need to do a spiral mold test. So we use microEDM procedure to generate dimples along this spiral track. So the first challenge with such a kind of mold, which has spiral shape, was to simulate the tool trajectory, because we have to drill dimples, we have to machine dimples along this trajectory, and it's not an easy process for such kind of Sarix machines microEDM operation. So we have to do it separately. So first we simulated this spiral using Archimedes equation in a MATLAB software, and there we simulated the dimples, and from there we extracted the coordinates which were fed into, let's say, the CAM program of this Sarix machine. So in total, we machined, let's say, 9 tracks with dimples of nominal diameter 50 micrometer and depth of 25 micrometer and a pitch of around 200 micrometer. So we can see in the video here the simulated, I think the video is not playing here. Okay, so this was the video showing the simulation of the tool path on the Sarix machine tool setup. Yeah, so here we can see the video, how the microEDM tool is traversing the trajectory of this spiral mold. Now, the next step was to prepare a tool that is able to give us, let's say, very accurate machining of the micro dimples. So here we can see we've initially used the 0.5 millimeter tool, and we reduced it to 50 micrometer tool diameter using on-machine wire electro discharge gracing technique, which is already available on our Sarix machine. So these were the parameters that were used for, let's say, dressing this tool for microEDM operation. So during the dressing operation, we found out that the process was not always very repeatable. So the dimensions of the dimples cannot be controlled very well. Secondly, the dressing time is quite high. It can take sometimes few hours because there are 3 steps involved. And this would take days to texture, let's say, a spiral mold. So the second approach we took was to utilize a commercial tool available in 50 micrometer nominal diameter. So here we can see that diameter of the dimples were very repeatable, but the problem was again with the depth. The depth of the dimple was not consistent, and this is because microEDM process has inherent longitudinal tool wear. So you can see here that we have a new tool after texturing, and after let's say 100 runs, 200 runs, 300 runs, and 500 runs, the tool gets shorter and shorter, and this will affect the depth and the repeatability of the process. So to, let's say, evaluate this, we quantified the tool wear on the machine. So first we can see a tool wear control. So we can see the length of the tool keeps on decreasing. The tool wear is quantified here in terms of longitudinal tool wear, that is decrease in the length of the tool. So we can see, let's say after 100 runs, the tool wear, the tool length reduces, and then we do automatic tool lengthening based on electrical touch, which is available on the Sarix machine itself. Then we have to lengthen it again. So although the process looks almost linear, but if we magnify it, this is highly non-linear. So if it was a linear, we could have made a simple model to do this, but this is not possible. So one of our colleagues came up with a new tool wear control technique. So where they call it run to run control. So what they did basically, here the problem is that when you drill from one dimple to another dimple, you change flushing conditions, you change sparking probability and other scenarios as well. Therefore, if we say that, okay, the tool wear in machining first dimple is around 30 micrometer, it would not be the same when you machine the second or third or fourth diameter. So it's not proportional. So therefore, our colleague designed a control system which is based on dynamically adjusting the open source voltage of the Sarix machine, as well as he introduced some tuning parameters in the control, let's say, algorithm, so that we can maintain constant longitudinal wear during all the experimental runs. So these were the parameters that were used for the, let's say, microEDM surface structuring. So these are the electrical parameters and also the servo parameters for the gap control. And then these are the results of texturing of spiral mold. So we can see this is the overview and optical image around, let's say, the middle of the spiral channel, and this is near the end of the trajectory of the spiral channel. So we can see quite nice micro dimples with very precise spacing and very good control of diameter. This was also evaluated let's say in terms of quantity here with the confocal microscopy. So we can see the top one was without tool wear control. That is, we just use automatic lengthening after, let's say, 100 dimples. So here we can see the depth is increasing. The depth of the dimples is not consistent. And this is because the tool gets shortened every time. So the depth gets increased. But when we use tool wear control, the depth of the dimples was quite consistent. And of course, the nominal diameter was 50 micrometer. But we also have side gap in the EDM process. So the hypothesized diameter was around 65 micrometer for these kind of dimples. So finally, the results of this were verified by using, let's say, spiral flow tests at our industrial partner Chromatic. And we observed that we can see the comparison here with the microEDM texturing. We got almost 27% increase in flow length as compared to unstructured mold surface. So you can see here the non-structured mold surface, then it's further increased by alumina blasting. It's a bit more increased by two-step blasting, which we saw in the initial slides. But with microEDM texturing, we are getting even more. So 20% reduction, let's say, as compared to unstructured mold surface. The next thing, which was also touched in the presentation of Zen, was because when we have to characterize the, let's say, the profile and dimensions of the surface roughness of the dimples, it's very time consuming to take this part out of the clamp and take it to a sensophore or a confocal microscope and then verify it there and then come it back, and then it will take additional time in referencing, reclamping, realigning the process. So one of our colleagues, he is already pursuing his PhD. He decided to put, let's say, a STIL sensor, it's chromatic confocal sensor, on the machine, and he's getting XY data from the encoders of the Sarix machine so that we can, let's say, measure the dimensions of the dimples on the machine itself. So, last contribution. The last contribution in this project was about a new mold material, which is wear resistant because it's a ceramic injection molding process. So after 5,000 shots, we are observing, let's say, great amount of wear with normal steel molds. So what we did, we first introduced a novel material from the materials department at KU Leuven here. So it was an niobium carbide metal sintered with a nickel binder. And here the blanks were then cut out of, let's say, with wire EDM operation. Then they were inserted into, let's say, the steel mold slides. And then we can see in the picture here. Now, the next challenge was to machine such a hard material because it has similar hardness to tungsten carbide, but a better toughness. So our industrial partner had to do, let's say, a lot of efforts in finding out the suitable parameters, suitable tools for machining such a material. Finally, with the CVD milling tools, they were able to machine, let's say, niobium carbide inserts, and we can see the insert with the 4 mold cavities. Now, the flow, let's say the moldability tests were performed using the niobium carbide molds at our industrial partner. And you can see the 36 caps manufactured, and we characterized the wear on the products because it was very difficult to characterize it on the mold itself. So we used, let's say, the product, the molded products, as a means to characterize the mold wear. So the 1 and the 3 indicate the cavity from which these products are coming out, and then the new indicates a new mold, followed by, let's say, the number of shots for which these products are produced. And we measured it using, let's say, Mitutoyo CMM, where we used, let's say, a ball probe of 1 millimeter diameter, and we characterized the outer diameter. Of course, we avoided the parting line of the products. Otherwise, this will cause errors in the measurement. So we can see here that from new to 2000 shots, we had, let's say, less than 12 micrometer wear. We assumed that the shrinkage was proportional across all shots. So the difference in diameter will give us the wear of the mold surface. So it was less than 12 micrometer, and which is very impressive figure as compared to the 200 micrometer, which we have seen on the steel molds, which were traditionally used at Formatec. So finally, the takeaway messages from this, let's say, ProSurf project, and also from these research activities, were that with the two-step microaggressive blasting, the reduction in injection pressure of around 150 bars was obtained. So this was leading to energy savings at our industrial partner. Similarly, microEDM structuring with run-to-run control of tool wear has the capability to generate consistent and controllable dimples. The structuring technique we used, the microEDM one, gave us 27% increase in spiral flow length. And also the niobium carbide mold material we used here is giving us less than 12 micrometer wear, or let's say the dimensional enlargement of the molded products. Thank you very much for your, let's say, attention, and I'm open for questions. And I would like to thank KO Leuven team as well as the Formatec team for assistance during this project. Thank you very much.